Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello or welcome back. If this is your first time watching one of my videos, then welcome to the series. My name is Roy Simpson and I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This is a continuation of a pre-calculus sequence of videos, pun intended. And we're right in a smack dab in the middle of sequences and series. And we've already talked about what a sequence is, what a summation is. You should have strong familiarity with some summation notation, what a partial sum is, all that fun stuff. And you should have watched my arithmetic sequences and summations video, mainly because that is the precursor to this video, and it helps understand a little bit of what's going on here. In this video, we'll concentrate on a new kind of sequence. We already did, like I said, arithmetic sequences. The most important kind of sequence for us is going to be geometric sequences. That is the kind of sequence that you find more often than not out in the real world. So let's talk about what a geometric sequence is. A geometric sequence is a sequence of the form A times AR times AR squared times AR cubed, and so on and so forth all the way down the line. If you notice, each time you're adding a term, or placing a term, I should say, into that sequence, you're actually just multiplying the previous term by r. So you get something that looks like this, and so on and so forth down the line. Very easy pattern, very nice. R itself is called the common ratio. So this r is constant throughout, and it is the common ratio. It is the common multiplier, if you will. And the nth term of the sequence is actually given by a sub n is equal to ar to the n minus 1. I consider a itself to be the initial value of the sequence, so let me label that. And there are a few things I want to note about this, because really this statement that the nth term is listed this way is a convention. In reality, really what you want is that the very first term of your sequence be the initial value a, and then the second term to be a times a common ratio. It actually does not necessarily always have to follow this format here. It will in your pre-calculus course, but you'll find in some of the examples I do that I'll showcase a different way to write these. But it is very, very important that the first we'll say the first term of your sequence has r to the 0th power. That is very important down the line when we start adding terms of this sequence together. It's actually somewhat critical. So for our first example, it is just a setup, just getting used to what a geometric sequence is, making sure we know how to list out terms, state the parts of a geometric sequence, that type of thing. So the nth term, they've given us the formula. When anybody tells you the nth term is given by, they're literally giving you the equation for that sequence. So we've been gifted this. Often you're not gifted that. The nth term of the sequence is given. Great. Find the first 5 terms of the sequence, the common ratio, and then graph a few terms. We'll graph them by hand. But then I'm going to showcase what this looks like using Desmos, because it's kind of important to know how to use Desmos in these situations. All right, so the first 5 terms. Well, that's not too terrible. I'm going to zoom in just because my pen usually messes up if I don't. So a sub 1 is equal to 5 halves times negative 1 half raised to the 1 minus 1. That's negative 1 half to the 0th. We know that any number raised to the 0th is just 1. And this actually matches the idea of the pattern, which is that this, let me point when I say this guy right here is A, and obviously, therefore, this guy must be R. And R is our common ratio, so I can immediately off to the side just say common ratio is going to be negative 1 half. And it's okay for our common ratio to be negative That's perfectly fine. In fact, it causes something called an alternation. So we will have, this is considered to be an alternating sequence, and we'll see it in action. This is one of the very popular styles of sequences and really subsequently series in Calc 2. So you're seeing a little bit of calculus here. A sub 2, negative 1 half, raised to the 2 minus 1, or raised to the first. And obviously a negative power raised to the first is going to be a negative, and then you have 5 halves times 1 half, which is 5 fourths. A sub 3, really from this point forward, I mean, I'm going to list it out like this just for a sub 3, but I really want you to pay attention to the fact that what's happening is every time that we go from one term to the next term, we're actually just multiplying by that common ratio. That's all we're really doing. So if you were to compute this a sub 3 right here, you'd have negative 1 half being squared, which is 1 fourth, times 5 halves, and so you'd have 5 over 8. But if you take a look at what would have happened had we just multiplied the previous term by a negative 1 half, you would have gotten a positive 5/8. And so that's kind of a shortcut to listing out terms. And that's kind of why in a textbook, they'll ask you to list out a few terms so you can see the pattern that all you're doing is multiplying. And remember with arithmetic sequences from our previous videos, arithmetic sequences had us adding that common difference. So we're adding D every single time. Here, we're multiplying by R every single time. So that is the difference between an arithmetic sequence and a geometric sequence. Let me erase that, get that out of our vision, but that's a good thing to note. So I'm going to go ahead and just take advantage of the fact that this is geometric, so I'm going to multiply by a negative 1 half every time. So my next term in line would be a negative 5/16. And then finally the fifth term is a positive 5/32. Again, because I'm multiplying by a negative 1 half. So that's a very fast way to list out the first 5 terms of that sequence. You can see that they're actually alternating. And what I mean by alternating is they go from positive to negative to positive to negative to positive. They're jumping back and forth between positive and negative, and that is considered to be an alternating sequence. It has to have that type of pattern, by the way, where it's every other one, it hops between positive and negative. It can't be positive for 5 terms and negative for the 6th, and positive for 5 terms and negative for the 6th. That would not be considered to be alternating. And we've actually pretty much completed the problem except graphing the first few terms. And we have the first few terms listed. So let's go ahead and by hand just graph them out. So I'll call this the n axis, and here's the y axis. N equals 1, 2, 3, and 4. And we'll just go to 5 because that's how many terms that we have. The deal here is, though, that we should probably have our y-axis go negative as well, because you could see that our outputs are going to be positive and negative. And our most positive output is 2.5. So I'm going to go ahead and say that this height right here is 5 halves, or 2.5. And if that's the case, just kind of eyeballing it, this is probably a negative 5 halves. So let's go ahead and start doing this. So it starts off, I'll plot these in blue, at a positive 5 halves when n is equal to 1. When n is equal to 2, it's negative that, but half. So negative 5 fourths. And then when n is 3, it's positive half of that. So it's positive, it's not 5 fourths, it's actually half of that, 5/8. So let me erase that blue right there. I'm just showcasing that. And then for n equals 4, it's again the opposite of that, but it's not a negative 5/8, it's half of that. So I have to kind of zoom in to get to the halfway point. So it's probably right about here, 5/16. And then when n is equal to 5, again, it's not exactly the opposite, it's half of the opposite. So it's a little bit closer. So every single time it pops back and forth between the n-axis on either side of the n-axis, and eventually it's getting really close to the n-axis. And this idea of something getting very close to an axis is going to be incredibly important for us. We already know that it's called a horizontal asymptote, but as time goes on, we're going to talk about the convergence of things, that type of thing. That happens in calculus, but it's good to have this nomenclature kind of on your plate right now. And here I am over in Desmos here, and I create, for sequences, you have to create a list of numbers. And to do that, you just let any variable, I use a capital N just because that's pretty common. A capital N equals, and you start a bracket, and you just say 1 ... to 20. That'll create 20 elements. I think there's another way to do this, by the way. I think you can do this using like 1, comma, ... comma 20. No, I guess not. I guess it's just 3 dots. 1, 2, 3, and then 20. Okay. So that creates 20 items. And then what I do is I plot points. The nth item, let's say n is equal 1. So the first item, and then the function or the sequence that we've been given. We've been given 5 halves times n negative 1/2 raised to the n minus 1. And notice I'm using these capital N's because the capital N is actually my list of numbers. I suppose I could have used lowercase n, actually. That's perfectly fine. Yeah, we could have done that. Okay, so you can see off to the right-hand side, and let me just shrink that back. You can see off to the right-hand side that this is the sequence itself. It's plotting it, right? There's my 1, 2.5. Right? You can see it's bouncing back and forth between the n-axis here. And you could also see that it's eventually getting really close to that n-axis. Notice it doesn't go beyond 20 because I only plotted out the first 20 numbers. There's no real need to go beyond that. If you zoom in, you can see, if you zoom in enough, I have to zoom in quite a bit, but you can see there is some airspace there, but it's super duper close to 0. So that's just a heads up that it is actually getting close to 0. It's not actually touching 0. And so there we go. That's how you could plot using Desmos. That's how you plot a sequence of values. Now in this example, we're not even told it's geometric. We're asked, is this sequence geometric? If it is, please find the common ratio. I'm going to list out the terms here. I know they're already listed, but I just want you to see kind of the idea behind the scenes. So we have 1/2, and the next one in line is 1/3, and the next one in line is 1/4, and the next one is 1/5, and ... That just means the pattern continues. Well, if it's geometric, that's a big if, but if this is a geometric sequence, then every time I go to the next number in line, I'm multiplying by a common ratio. And that common ratio should stay constant, actually. It's common to all of these. If, big fat if it's geometric. So let's ask, what would I multiply 1/2 by so that I can get it to be 1/3? This is how you kind of start these problems if it's not obvious. I'll tell you right now, this one's somewhat obvious. Most students will pick up on this very quickly, but it's still a good question to ask. How would I get from 1/2 all the way to 1/3 through a multiplication? Well, you multiply both sides by 2, and that tells me that r is equal to 2/3. If you're hearing a bird in the background, I just live in the woods, and so there's a bird in the background. They're busy this time of year. So I'm going to go ahead and say, therefore, that this common ratio, at least this r right here, has to be 2/3. Well, that's a little bulky, so let me make that a bit larger, 2/3. Great. So let's see if I multiplied by 2/3. Say, does that equal 2/3 there? Well, let's see. 2/3 times 1/3, this 1/3 right here, would not become 1/4. 2/3 times that 1/3, that this guy right here. We want to get to 1/4, but this is actually not 1/4. This is 2/9, which is not equal to 1/4. And so this sequence is not geometric. Every step of the way, you're not multiplying by a common number, because we multiply by 2/3 to get from the first term to the second. We'd have to multiply again by 2/3 to get from the second term to the third term, but that just didn't work out. So this, I'm going to just say, is not geometric. And I introduced proper English there as well. So not a geometric sequence. All right. Well, let's try this again. Determine whether the sequence is geometric. Now remember, the prerequisite for this material is that you've already gone through a lot of your pre-calculus course. Most students actually, most pre-calculus courses have already gone through everything in pre-calculus by the time they get to this material. What I find is that sequences and series are better treated early on in a pre-calculus course after you have gone through exponentials and logarithms, because you don't really need anything else. You don't need your trigonometry. And so I like to treat it somewhat early, maybe about the first third or half of the course, because this is probably, honestly, the most important material in pre-calculus. So to master this is incredible, or is incredibly important. The reason why I say that is because I'm assuming you already know how to work with logarithms and properties of logarithms. So let me write down this sequence for myself. So I have the natural log of 2, and then I have the natural log of 4, and then the natural log of 16, and the natural log of 256. And they say that's a pattern. What you need to do is figure out, how the heck is that a pattern? Well, note that each of these, at least the arguments for the logarithms, are powers of 2. That's natural log of 2 squared. This is the natural log of 2 to the 4th. And this is the natural log of 2 to the 8th, actually. And dot, dot, dot. And that can be written as 1 times the natural log of 2. And this can be written as 2, because you know the properties of logarithms that you can bring out this exponent. So it's 2 times the natural log of 2. Next one is 4 times the natural log of 2. And the next one is 8 times the natural log of 2. So it does take a little bit of skill to see patterns, but patterns are incredibly important as you move into calculus. And so I really encourage my students, pay attention to patterns. Really try to see things within the mathematics. And there's even one extra little pattern here that I don't know if you're going to see, but let's see if you do. All right, so actually, maybe I should just say it this way. If this is geometric, we would be multiplying by the same number every single time to get the next one in line. And if you look, getting from the first term, which is 1 natural log of 2, this guy right here, to the second term, which is 2 natural log of 2, we would have just multiplied by 2. So I'll say this is equal to 2 there. The question is, getting from the second term, 2 natural log of 2, to the third term, 4 natural log of 2, did we multiply by that same common ratio? And the answer is yes. We totally multiplied by yet another 2. So I'll go ahead and write that in. And you can see we multiply by 2 to get from 4 natural log of 2 to 8 natural log of 2. So this tells me the common ratio is 2. I already know it. So we found the common ratio, and actually that's all they ask. But you know what I'm going to do? I'm actually going to go ahead and write the actual sequence. Like, what is the pattern for the sequence? Maybe I should write it down below. Well, we know that our common ratio is 2. So 2 to the n minus 1. We just need to write down our starting value, right? Because remember, the formula for a geometric sequence is this, where a is the initial value and r is the common ratio. We already found the common ratio to be 2. And if you look at our sequence, the initial value is the natural log of 2. So I'm going to go ahead and write in the natural log of 2 here. And you could test this against the sequence we wrote out there. I'll usually just go maybe to the, let's say the 4th term here. Let me highlight that. I'll go to that 4th term of the sequence and I'll try it out. A sub 4, let me use my pen here. A sub 4, according to the pattern that we wrote out, is natural log of 2 times 2 to the 4 minus 1, which is 3. That's 8 natural log of 2, and that totally does match this right here. So we do have the pattern locked in. The pattern, even though they didn't ask for it, is this right here. All right, so being able to spot those patterns and name the actual sequence is very important. So practice those. Now, if you've been watching my videos for pre-calculus, you probably have noticed that I don't really teach, I more review as I go through, because in pre-calculus there's just a lot of stuff you've seen before, so I can kind of quickly go through. If you need to be taught something, you can review my Algebra 2 videos or my trig videos or something like that. But this you should never have seen before, and so that's why I'm taking my time. There's a lot more examples here so that we can kind of really nail down what these ideas are. So in this sequence of numbers, we're asked to determine the common ratio, which means they're implying immediately that this is a geometric sequence. So determine the common ratio, the fifth term, and then the nth term of this geometric sequence. Well, let's go ahead and list them out. I like to stack them if you haven't noticed. I like to write them as stacked values. So I'm going to go ahead and do that here. 0.3 and a negative 0.09 and a positive 0.027. You could see it's alternating, right? Negative 0.0081. So let's see, if it's alternating, I know that my sequence is going to have a negative 1 to a power. But let's go ahead and just start by saying, how did I get from here to the second term? What did I multiply by? Well, R in this case is going to be a negative value. And then let's see, what would you multiply 3 by to get to 9 first? Normally you'd multiply it by 3. But 0.3 times 3 is 0.9. So that's not going to be good. We need to actually shrink that number a little bit. So let me go ahead and multiply it by 0.3. If you multiply 0.3 by 0.3, it does become 0.09. And then the negative, of course, will make it a negative 0.09. So let's go ahead and try that again. Let's see if that same common ratio holds. Let's see, if you multiply negative 0.09 by a negative 0.3, you will get a positive 0.27. So looks as though we're good. I mean, you could check here as well if you want to, but it is going to hold that you're multiplying by a negative 0.3. So I immediately know that the sequence is defined by the formula a sub n is equal to the very first term times the common ratio raised to the n minus first power. Let me zoom in so my pen doesn't do that. I'll zoom out. All right, and what else were we asked? Determine the common ratio, the fifth term. Well, okay. The fifth term, we already have 4 of them. So that's kind of a silly question, but you could totally determine the fifth term by multiplying this value by, again, a negative 0.3, which ends up being a 0.00243. So there you go. Keeps going down by 3/10, basically. You're multiplying by 3/10 every single time. So yeah, that's actually the complete part of this question. So again, all we're dealing with right now is geometric sequences. If you have already read the section that you're in and you're like, I'm working on geometric series, that's in another video. As a final example here, I want to illustrate something that you already know, but from previous work, but I want to say it out loud here. This is, I had mentioned it before in the arithmetic sequence video. In fact, I concentrated on it there, and I haven't really said it here, so I apologize. But arithmetic sequences have the form a sub n equals d times n minus 1 plus a. And a is our initial value and d is our common difference. And I said in those videos that this is very much like having a line. F of x is equal to mx plus b. B would be considered our horizontal or vertical intercept, so that's our initial value, and m is our slope. Every time that you move x forward by a step of 1, the y values get multiplied by the slope, just like every time you increase your n values by 1 with an arithmetic sequence, you're adding this common difference. So in both cases, you're just adding the same number step by step. But now we're dealing with something significantly different, but still has some commonality here. So I'm going to draw a parallel to something that you should have already covered in your pre-calculus course. Now we know that the geometric sequence has this form, a sub n equals the initial value and then some common ratio to a power. Well, if you relate that to the algebra you've been working on, you might see that this is very much similar to this. Just like an exponential function, it has an initial population, just like you have an initial value. And every time a year passes, or whatever t may stand for, you're multiplying by the base. And that's exactly what we do here. Every time we increase n, we're multiplying by that base, which is the common ratio. So this is geometric series, or sequences, sorry, I was trying to avoid saying series. So geometric sequences are to exponential functions as arithmetic sequences are to linear functions. In fact, that's so important, I want to write that down. So there you have it. Geometric sequences are to exponential functions as arithmetic sequences are to linear functions. That is a mantra that is so important to realize. And again, in calculus, you're going to be playing with geometric sequences quite often, in fact. So it's important to really get to know this stuff. And these videos will be online, hopefully until YouTube closes its doors. And so you can always revisit this stuff when you get in your Calculus 2 course, because you're going to have a semester away from geometric sequences after your pre-calculus course. So being able to bookmark these, come back, will help out. Now, I went through all that because this example relies heavily upon our ability to find the equation of an exponential function given 2 points. Remember, geometric sequences are kind of like exponential functions. And so finding the equation or the formula for a geometric sequence will be very similar to finding the function for an exponential function had you been given 2 points. So in this case, they're telling us the second term, which I'm going to write as a point, and the fifth terms, which I'm going to write as a point, are 10 and 1250 respectively. So 2 goes to 10 and 5 goes to 1250. And by the way, that just means a sub 2 is equal to 10 and a sub 5 is equal to 1250. I just like to write them as points because it really allows me to see, yes, these definitely mimic a function. There's an input and an output. All right, so is 31,250 a term of this geometric sequence? If so, which term is it? Okay, well, let's first find a formula for this geometric sequence. Now remember, if it was an exponential function, we could find the formula just by plugging in these points. We happen to know the output is 10 when the input is 2. And we know the output is 1250 when the input for our geometric sequence is 5. Notice what I did. All I did was just take the formula. That was supposed to be blue ink. Sorry about that. I took the general formula for a geometric sequence, this guy right here, and I plugged in 10 for my output here and 2 for my input. So that's all and then I repeated that process with 5 and 1250. So that's all I'm doing. And then I had mentioned, if you watch my videos on exponential functions and actually finding the equations for exponential functions given 2 points, the way that I do it is I create a system. So let's go ahead and create a system out of these two. You don't have to. You could solve one equation for a variable and so on and so forth. But I tend to like to do it this way. This is 10 is equal to AR to the first, and 1250 is equal to AR to the fourth. And then I will take the one with the greatest power on R. So this is, I'll call it row 2. and this is row 1. I'll take row 2 and divide it by row 1. If you don't want to do it this way, if you want to just take row 1 and solve it for A or R, more power to you. I just don't do it that way. You could totally do it that way though. I have no qualms with that. But taking row 2, which is 1250, and AR to the 4th, that was supposed to be a 4, and dividing that by row 1, you see something very special happen. On the right hand side, the A's will cancel out. So you're honestly solving specifically for R here. You have 125 is equal to R to the 3rd. Well, I happen to know that 5 to the 3rd is 125, so that means that R is equal to 5. Once I find that, I can go to either of these formulas and substitute in 5 for R. I think you know which one I'm going to use. If I substitute 5 into that, it's super easy, right? A will be 2. So I go ahead and do that. I'll even write that out so I don't skip that step, but this implies 10 is equal to A times 5, or in other words, A is equal to 2. And now I have my entire formula that, let's see, I'm going to write this down below. A sub n is equal to 2 times R, which is 5, to the n minus 1. Now, all that work, and you think you're done. This sequence, specifically this geometric sequence, contains the points 2, 10, and 5, 12, 50. But that wasn't really the question at hand. The question at hand is 31,250 a term of this sequence? And if so, which term is it? Well, if it's a term of the sequence, then the left-hand side here should eventually become 31,250. So let's go ahead and solve and see if that can happen. 31,250 is equal to 2 times 5 to the n minus first power. Well, dividing both sides by 2, you'll get, and you can hear the clickety-clackety of my calculator because I'm actually doing that, you get the following. 15,625 is equal to 5 to the n minus first power. Now, you can solve this exponential equation by going ahead and taking the logarithm of both sides if you want. And just as a reminder, it is an exponential equation because your unknown is in the exponent. So that is critical to note there. I'll take the natural log of both sides, just because that's a habit that I have. So I'll take the natural log of 15,625. That should equal the quantity n minus 1 times the natural log of 5. If you don't know how I got that, watch my videos on solving exponential equations. Divide both sides by the natural log of 5. And also, when you're done with this, add 1 to both sides. So I'm just quickly kind of doing that. Plus 1 is equal to n. And then, if this becomes a natural number, like 20 or something like that, then you know that this is part of your geometric sequence. So let's go ahead and find out. And putting this all into a calculator all at once, not rounding or anything like that, because if you round, you'll get this wrong. So typing all of this into a calculator all at once, I get the following: 7. Because n is a natural number, that means there is a point when our geometric sequence will become 31,250. And that point is at n equals 7. The 7th term of this geometric sequence will be 31,250. So the answer to the original question, is that a term of this sequence? If so, which term is it? The answer to that is, heck yeah. Yes, it's the 7th term. And this is important to note. You could have, I suppose, just found out the common ratio, which we did, it was 5, and just started multiplying 1250 by sets of 5. 1250 times 5 would be, and now I'm going to do that, 1250 times 5 will get you to 6,250, so that's the 6th term. and multiplying that by 5 would immediately get you to 31,250. However, it won't always be that easy, so it's better to go about it the way we went through in this entire problem, because you don't want to have a kind of a trick method to get neighboring values when you hit an exam and your professor gives you something that requires you to go 57 values beyond there. So basically what I'm saying is you should really be decent with the method I've written here. This is a really solid method for finding out which term of a sequence this given value is. All right, that's all I have for this video. In the next video, we're going to start our conversation about partial sums of geometric sequences, and then we'll go into infinite series after that.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.